Okay, welcome back. And we are going to deal with the parts of the notes that we skipped the last time. Just so that I don't forget to say, I sent an email about I got the exam date wrong in the earlier email, and I've already corrected it. Did you all see that email? Okay, you gotta check your emails that come from me, okay? Because sometimes, I mean, I try to be as immaculate as possible, but sometimes I do get dates mixed up because I have multiple sections and all that. So it's not Thursday, the exam is not Thursday, next Thursday, all right? So we are going to talk about how do we sample from a finite population in the first place. So there are a few ways you can sample, and I'll talk briefly about each one. The first one is a non-random way to sample. It's called a convenience sample. Why is it called that? A sampling method is called convenience if it is non-random. So a good example of a convenience sample would be yours. If I wanted to know something about hope, and I just asked you all, just because you all are in the room now and it's easy, then I'll get some data from you. Now that sample is hardly random because you all are a captive audience. It's just convenient to ask all of you. So that's a classic example. This is very often done by Hope students because there's no choice. And I don't mind. For projects, you can use convenience samples. You can. I'm not saying that you cannot because I understand the limitations that you. The best kind of sample is a simple random sample, which we will get to. What's stratified sampling? Stratified sampling is another way to sample where what you do is you have your population, you cut them, you break your population up into groups or strata. Have you ever heard the word strata before? Like it's I think it's a kind of food actually. I've seen help serve strata or something like that. They have a lasagna is an example of strata. So you have different layers. So you layer your population by some variable. Usually it's maybe it's ethnicity, maybe it's age, or what you find a variable that breaks your population up into groups. Then in each group you sample. Now the whole purpose of doing that is to ensure that your sample is as representative because everyone wants representative samples. Who wants a sample that's not representative? And that's the problem with convenience sampling. This is not very representative of hope. A good way to tell why this is not a good representation of hope is the proportion of females in this class is not the hope proportion. So see, so convenience sampling can be dangerous because it can lead to biased conclusions. But we'll talk more about that. So we will not talk anymore about stratified sampling because the math around stratified sampling is quite complicated. So we will not play with this anymore. But we'll talk about simple random sampling a little bit. Simple random sampling is actually the best way to get a sample if you want to get one. All right. And does anyone have any ideas? How would you go about? I'm not asking you to do it, but how would you go about trying to get a simple random sample of Hope students? Anyone have any ideas? What could you do? Right. If you send out a survey, how do you make sure that it's received randomly by people? Anyone have any ideas?
Yeah. You could send out a survey to like all Hope students and give like a reward for completing it.
Okay, that's a very good idea. Do you know that when you give people an incentive to complete a survey, not that an incentive is a bad thing, it results in a non-random sample. You know what? You're attracting people who want the incentive. But that's a very good answer. Thank you. Anyone? Yes. Probably like yes, I would say simple enough. Go to shop setting up. Everyone has to eat. Okay. I wouldn't even say go to the library because not every student spends time in the library. So that's not random. But Phelps, pretty good. Right, I would say. Now, there used to be a time long before you all were in Hope where Cook only was accessible to people who were not freshmen or something like that. Or maybe not even freshman, sophomore. But anyway, all that's gone now. So Cook was not a good example of getting a random sample either. Phelps is. Good. Okay, so these are ideas. I actually had students do this and I don't recommend you do. They spam all of Hope, to get a random sample. They did it. Okay, A, they close their eyes typed in A, Google will recommend, and then they just randomly pick someone with the name A and all that. They actually did that. Now, please don't do that, okay? I don't believe in spamming, so don't do that, but there is a way to get a random sample of Hope students. All right, so that's the idea. So I think the time has come to revise some definitions. There might be some confusion about this because I've talked to some students. Do not confuse the two P's. Don't confuse the population and the parameter. Don't confuse the sample and the statistic. A population is not a number, okay? A population is a collection of things. The things technically are called observational units. Why do we use this strange term? Is because they are not always things that are physical. Yes, sometimes your population is made up of people, animals, plants, but they can be a population of free flows as well. Populations can be abstract. It might not always be a thing. So anything that you observe is called an observational unit. You see, that's why there's a necessity to say this. You can't say thing because a free flow is not really a thing. It's not something that you can touch, but it's an observational unit. So it's the entire capture observation. So that's what the population is. Does anyone remember what a parameter is? I think that's the next word that's going to come up. First of all, is a parameter a number? Notice I'm not asking you whether it's known. Is a parameter a number in the first place? Yes, a parameter is a number. But is it known? No, it's not known. Why? Because a parameter is a number that summarizes the population. P with P, right? Oh, I didn't go with, sorry. Okay, we went to sample first. A sample is a subset of the population, right? We know that. So we have already answered this. A parameter is a long run numerical summary of the population. And so far, how many parameters have I introduced? I've introduced 2. What was the first parameter I introduced to you? What number was it? A long run? Yes, pi. Good, you gave me the symbol. And what's pi? It's a long run proportion. Was there another parameter we introduced last week? This one starts with an M. It's a long run mean. That's right. See, a population can have many features. It doesn't always have to be a proportion either. I mean, if you think about all of hope, right? All of hope is a population. Can you think of a proportion of interest? Yes. What's the proportion of hope students that are left-handed? That's a proportion. What's the long run mean height of hope students now? Something like, so these are different numbers, but they come from the population. So they are different parameters. A parameter basically is a number that summarizes the population. So therefore, what's a statistic? Can you change a word? Statistic is a numerical summary of the sample, S with S. That's how you learn it. See? A numerical summary of the sample. So, what actually is a simple random sample? It is a method for choosing a sample from a population so that each member of that population has equal probability of being chosen. Now, there are a lot of words there, but I don't think it's that hard to understand. What makes a sample random is the fact that everyone potentially has the same likelihood of being chosen. Not saying everyone will be chosen, of course. That's not what sampling is. But everyone has the equal likelihood of being selected. Have you all seen how people actually generate random numbers? You know, bingo, they have all those balls in the cage, and then they turn the cage around, and then one ball pops up and things like that. That's actually trying to replicate the equal probability of a number coming up. All right? That's a way. So this is an ideal. It is very difficult to achieve. See, the idea we had of incentivizing people to fill in a survey will make it not equal probability of attracting everybody because some people just don't care about incentives. See, so it's very tricky to try to get a simple random sample. It's very hard. Even with this bingo ping pong ball method, it might not be. If you check history, uh, the Vietnam War was a highly divisive time in this country. If you think the country is divided now, you haven't seen anything yet. All right. The Vietnam War was one of those, I think it almost tore the country apart because there were debates on every side of that issue. And one thing was they had the draft, you see, And how did they decide who it was random? Or they thought so. There is now evidence to show that the selection of people to be drafted to join to be in the military was not truly random. It was slightly biased to people who were born earlier. In fact, that's where the phrase "your number is up" came from, because your number, your birth, basically it went by if you are randomly selected according to your birth month and date, you have to report for duty, or not, it would be a crime. And then, so there were people who defected to Canada and all kinds of things like that. But you can go read about it. But the thing is, I'm talking about the sampling aspect. They thought it was randomly generating birthdays. It wasn't. So even that context, it was hard to get a simple random sample. All right. Okay. So that's just an example. Now we've gone through some of these slides. What's the mean? We know that we know how to find a mean. And we also taught you the median. I don't want to go through this again. We've taught you how to get the median last week. We talked about skewness. We introduced this. This is very important. We taught you how to get a standardized statistic now to test for a mean. Now, I'm using colors because I want to show you the similarity. It's red minus blue over green. But now, because this is for a mean, it's not pi anymore, it's mu. We have introduced this new symbol for the population mean. It's also Greek. Remember, we use Greek letters for things that we don't know, that we hypothesize. We use English letters for things that we can see and measure. So that's x bar. Do you see the parallel with p hat minus pi? This is x bar minus mu, because you are dealing with a totally different paradigm now, if you like. All right. And the bottom is some kind of variability thing. I just colored it green. Whether that comes from simulation or from a formula, it's green. I'm trying to, maybe not so subtly, show you that everything in statistics is linked. They are very similar concepts, but you must be very aware now. It's like there's a fork in the road. Are you on the proportion road or are you on a mean road? Because the two analyses are different. As I have stressed, and I will show you in the next slide, we have learned how to use a simulation-based test for proportions. That was the first thing we taught you. You know, the applet with the coin tossing, and the spinner and all those. Yes, we have done that many times. So you go to the one proportion applet, then you have to put in the pi value, and then you spin or you flip the coin, get the null distribution and all those good things. So we have done that many times. This is the simulation way to do inference for a proportion. And you can calculate sim z or get a p-value. Right? We will be revising all these things today. Right? But this was for a proportion. There was simulation. I then also introduced this statistic. I know it's very small, so I think you have probably seen this many times by now. I don't know why Google does this to me. I don't want this page and they bring me there. Terrible. Okay. Okay. We've also learned this one. Remember theory Z? Why is it called theory Z? Because it's not simulation. This is entirely formula based. You don't need any simulation. You use a formula for the denominator. Okay, so see p hat minus pi, red minus blue over green. Same thing. Then, last week, we introduced how do you get a statistic for comparing a mean? And this is the one I just talked about, like 2 minutes ago. X bar minus mu divided by S over root n. And then, see, I say where mu is what the null says it is. Don't worry, we're going to revise all these things. I'm just putting it out there that you should know 3 things now. I do say here, X bar and S are either given to us or calculated from software. Remember I taught you how to use Google Sheets to find means and all that? Let me revise with you. Does anyone remember I don't know what's the word for it, the command. Yeah, the command for getting a mean in Google Sheets. Does anyone remember what you should do? You go to an empty cell, you type equals what? Very good. Average. Very good. What about S? How do you get the standard deviation. How do you get Google Sheets to tell you the standard deviation? What was the command for the standard deviation? Anyone remember? Yes. Perfect. Yes. Remember? Right? The STDEV. Right? STDEV. Just remember, right? Something unpronounceable, right? That's the one. That's what I mean by X bar and S are given to us by software. Nobody wants to count it by hand. You can, but I don't recommend it. It's very slow. You can use a calculator. There's a formula, of course. But we use software, or I give it to you on exams. And yeah, that's it. So 3 things. So let me summarize this on the board for you. If I can. Why is there not even one? Oh, this is terrible. There was a pen here and now it's gone. Well, there are 3 things you need to have clear in your mind. There is SIMZ, there is theory Z, and there's theory T. Just these 3 things. Do you notice? Yes. Oh, thank you. Please remind me to give back to you. Thank you. So there are 3 things for proportions. I have taught you 2 ways to do inference. If you go the simulation route, then there's the formula for SIMZ. I don't want to write it for a reason, because you should know this by now. We also introduced theory Z, did we not? And it's on the screen now. Now there is another thing for means, because the means and proportions are different. This one, I only taught you theory T. So I think someone's going to ask me, why is there no SIMT? Well, there is, but here's something a little bit scandalous, okay? I don't agree with that pedagogy, honestly. As a statistician, I don't like it. So I don't teach students in my section. Your friends in other sections may learn it. So don't be surprised if you say, I learned how to do simulation for means. I don't agree with that approach. And so I don't teach. That's why there's an asymmetry here. That's why this one only has one method. All right. 3 formulas for today. So have it straight in your mind, okay? Okay. Let's go on. For categorical data, we are typically interested in a long-run proportion of something. And you have correctly said that the long-run proportion symbol is pi. All right? Notice I've kept this part blank because it depends what you're interested in. What are you interested in? Proportion of what? The long-run proportion of Hope students who are left-handed. The long-run proportion of Hope students who were born in Michigan. The long-run proportion of Michiganders who like snow, whatever it is. So something, right? So I left this blank because you fill in the blank. Depends on what you want, but it's a proportion and it's long run. So notice I say for categorical data, what's categorical data? Categorical data are basically for this intent and purpose, binary. It's a yes or no question. Are you born in Michigan? Yes or no? Do you like snow? Yes or no? Okay, so yes or no questions lead to proportions. Are you left-handed or not? And things like that. So categorical data leads naturally to proportions, and we have done this since day 1. The observed proportion is called p hat. Why is it used in English letter? Because you observe it. Anything you observe is p hat, and we try normally to give colors to things. What do I color pi? What do I color the unknown pi, actually, always, all this while? There's only a few colors we've talked about. Does anyone remember? What's the color we associate with pi? The one that you hypothesize and say things about. Maybe I'll ask a simpler question. What color do we use for p hat, the observed statistic? Red. And therefore, pi will be? Remember that. Okay? Then you can get what's called the p-value to see how likely are you to get something more extreme. What's the color we associate with the p-value, that fraction? Purple. Very good. There's nothing new here. I'm just summarizing what we've done. If validity conditions are met, you can use theory Z. See, that's the second thing. So I'm talking about sim first, now theory. Theory Z is a very similar formula to sim Z. Does anyone remember what the validity conditions are? You needed to have something true about your sample. Does anyone remember how it sounds like? What did the validity conditions sound like that I introduced the last time? You can't always use theory Z. There's a disclaimer. Does anyone remember what it sounds? Yes. Yes. You needed at least 10 successes and at least 10 failures in your sample. Remember this? Now, is it natural to you why you can have things like successes and failures when you have a categorical thing? Of course, if you ask people, are you born in Michigan or not? You're going to get a yes or no. Can you count how many yeses you have, how many no's you have? Of course. So successes and failures occur naturally with categorical data. That's why this validity condition is an easy one. You just need to check, do you have at least 10 people who are yeses and at least 10 people who are no's? If you don't, you should not use theory Z. You should simulate. You see? And again, you shouldn't. It's not that the formula doesn't work when you don't meet VCs. There's nothing wrong with the formula. The formula will work, but you shouldn't use it. It's kind of like, can you eat a whole birthday cake? You can, but you shouldn't. So that's the difference between the two words. You can, but there are many things you can do that you shouldn't. Okay? Can you go out in the cold and wear one layer or something? You can, but you shouldn't. You probably get a bad cold or something like that. So, can you use theory Z when you don't meet the VC? Yeah, the formula is not going to wrong. The formula doesn't care, but you shouldn't because the conclusions you get may be a bit out. All right. Okay, good. Now we come to, well, what happens if you have quantitative data? When you have quantitative data, you tend to be interested in a mean. And notice I say, first of all, the symbol is different. Mean, mu. Unknown mean, Greek letter mu. Long run mean dash. Why is there a dash? Because I don't know what scenario you're talking about. What are you talking about? You must have some quantity that comes after the word mean. Are you talking about a mean height? Are you talking about a mean weight? Are you talking about a mean amount of money you have in your pocket or whatever? What mean what? What do you mean when you say mean? So it's not complete to say. Some people say this, Oh, mu is the long run mean of Hope students. Yeah, what about Hope students? When professors see things like that, it really makes our heart ache a little bit because the long run mean of Hope students. Yeah, mean what? What? There are a million things you could measure quantitatively about Hope students. Yeah, what about the Hope? You must say mean height, mean weight, mean number of credits they're taking, or whatever it is. So there should be something sitting next to this word mean, and then it's completely defined. Then, when you have quantitative data, can you calculate a sample mean X bar? See? So we have reached a stage now where we have a multiplicity of symbols. It is very, very important that you keep them all straight. Here are your two observed statistics. This is the observed what? What's the word for this? This is an observed proportion, P, at observed. This is observed sample. Both of these are statistics because they come from a sample, but this is specifically, this is an observed proportion, and this is an observed mean. And the population counterpart, not the same thing, is pi and mu. So 4 symbols, don't mix them up. This is also a proportion, but it belongs to the population, and we don't know it typically. Mu is also a parameter. It's a mean, but it belongs to the population, and we don't know it. That's why this is the Greek P, and this is the Greek M. So keep them straight. Then we have talked about this a bunch of times. You have your theory T, right? X bar minus mu divided by S over root n. Let me show you very quickly where this comes from. Remember, we did this last week. I asked you all to contribute to Scratchpad. let me, okay, I think it's here. Yeah, see, we pasted it here. Remember, we got everyone in the class to tell how many hours they slept last night or something like that. So we got the sample mean from the class, we got S from the class, and then we calculated, hey, here's a reminder, X bar minus mu. For some reason, I want to test mu is 6. It can be something else. I want to test mu is 6, so I use 6 here. And then you have the SB and square roots and all that. So that's what we had the last time. So this is the formula that I was talking about in my slides here. There's one thing new on this page which I want to introduce, and that is the VC. Every theoretical test has a VC attached to it. Now we have seen that for theory Z, your VC sounds like this. You need at least 10 successes and you need at least 10 fails, if you remember. For theory T, the VCs sound different. The VCs are you need at least 20 observations, and when you plot the observations on some kind of dot plot or histogram, there should not be much skewness. It should be like a bell. Let me ask a question to the class, and I'm confident someone will know the answer. Why do the VC sound different for this? Why is there no success failure word here? Anyone can tell me why? This is a different VC. This is for quantitative data. Why is there no mention of successes and failures for the VCs? And why do the VCs sound different? Does anyone know why? Anyone want to try? Why do the VCs sound different in the case of quantitative data? Yes.
Some data, or like people could say yes to multiple things, or no to multiple things. It's not binary.
Yes. Quantitative data is not binary. When you don't have a binary question, what is a success? There's no meaning to say a success when your data is non-binary. If someone asks you, how tall are you? Do you say yes? How tall are you? Yes. How old are you? Yes. No, these are non-binary questions. And so when you have a non-binary answer, it makes no sense of a success or failure. How tall are you? I don't know. If someone says, okay, I'm 170 something 7. How is that a success or failure? It's quantitative. That is why it sounds different. Good. So the VCs match the data type. Quantitative data leads to this kind of VC. Is this okay? All right. So copy these things down because they are important. One last thing we'll talk about on this slide. Remember we introduced medians the last time, and then after this slide is over, I'll give out a worksheet to do. All right, where we will ask you to do all these 3 things. So remember we discussed medians the last time. Here's a simple example. I'm trying to tell the class that medians have a very special superpower. They are quite resistant. Let me explain what it means. What's the median of the set 1, 2, 3, 4, 5? Anyone? What's the median of 1, 2, 3, 4, 5? 3, right? Middle. This is sorted already. What is the median of 1, 2, 3, 4, 500? Also 3. So do you see that the median stays unchanged even when you replace a value with a very extreme value? So the moral of the story is the median is called resistant. It is something that is largely unaffected by extreme values on either side. If you put a very small value here or a very large value on the other end, the median happily stays in the middle. That's why the median is quite a popular statistic that's used to summarize where the middle is. Would you agree that the mean is very badly affected by this one? Yes, the mean, the presence of, you can think of this as like salaries, for example. Everyone in the US has been introduced to the word oligarch now, right? So if you put an oligarch salary here, won't that affect the mean? Of course, but it doesn't affect the median. And that's why you hear things like median income of household, because we all know that there are extremes in every data set. So the median is very stable. I will say one last thing though. Why do we emphasize on the mean so much? It's because the median, while it is a very good measure, it's very hard to play with mathematically. It's a very prickly mathematical object. It doesn't have nice, simple formulas like theory T, which involve the mean. That's why the median is not so popular in statistics class. It's very popular in used as a descriptive statistic for data sets. Yes. That's why you see median salary in America, for example. But it is very hard to use analytically. That's why we teach you the mean so much. Although the mean is severely affected by extreme values. All right? Okay, this is a perfect time for me to give out the worksheet for today. Please bear in mind, I mean, it's pretty obvious. There are three things here, and there are three parts of the question. All right? I want to do it this way. Can I have you all, can I have you all do one, can I have you do one part first? We'll discuss, then we continue. All right? Okay. The first one I want to discuss is this one. So you do it first. Do it on paper first. Give it your best shot, and then we'll discuss. Then we'll move on. All right. Maybe I'll have the class just answer me this. When you have a question like this, talking about the multi-generational hope student thing, first of all, are we in a proportion mode or are we in the mean? What situation are we in? Proportion. Why? Because it's binary. You are either a multi-generational hope student or you're not. I mean, notice I didn't ask how multi-generational you are. That could be a thing. Do you know, in all my years teaching here, the highest I had was a student with level four generations consecutively, I think. Oh, do you all know anyone higher than that? Four? Anyone knows anyone more than four? I've never had a student more than four. I try to analyze every class that I teach. I've never had one more than four. But anyway, that's what multi-generational means. Okay, so this is a proportion problem, first of all, which means you should be looking at proportion things. All right. So let me copy this. Let me copy this onto Scratchpad so we can work on it together. Now, I think something has happened. If someone would be so kind, I think this has mistakenly gone into the header. This happens sometimes on Google Docs. Can someone take it out of the header, please? Because I think it shouldn't be there, right? And I'm not sure how to do it, right? I think that picture went into the header somehow. Thank you. All right. Okay, let me help you out here. It's a proportion problem. So this will be the long run proportion. Can you finish the sentence? Thank you. I was just about to get there. Thank you. Anyone know what I'm getting at? Remember, I gave you the slide long run proportion blank. Can you fill in the blank appropriately here? What's in this context? The long run proportion of students at home. And what about them? You must, who are That's right. Perfect. That's it. That is it. And what's the symbol we use for a long run proportion? It's on the board. Every time you see long run proportion, the symbol is pi. Why? Because is this known? Do we know the long run proportion of hope students that are multi-generational? No, no one knows. You see? It's a number, but no one knows. Okay. Let me ask you something. And I want to see whether you are very able to pick this up. Do we mean pi to be this? Now be careful, okay? Or which is it? I want you, they're both pi. I want you to strike through, don't delete. I want you to strike through the one that we are not interested in. This is important. Which definition is actually correct? Is it the long run proportion of currently Hope students who are multi-generation now? Or is it the long run proportion that are multi-generational 20 years ago? Which is the correct definition of pi, actually? Anyone know what I'm saying? Can you strike through, don't delete. Can you strike through the one that we are not interested in? So this is not such a straightforward problem, is it? Okay, which is the definition of pi that we want? It's very important. What's the definition of pi? Is it now or 20 years ago? Very good. We are not defining pi as 20 years ago. Do you know why? Because this is being used as status quo, we are comparing what it is now to what it was last time. Now, of course, 20 years ago, there was a long run proportion that can also be called pi, but we are not interested in that right now. Is it clear? That's why I want to put the word now there. They are both pi, they are both proportions, but we are not interested in this. So I don't want the class to be confused because there is a point where some people think, but didn't you say it was 20 years ago? Yeah, we are not testing that. I'm telling you, 20 years ago, 35% were multi-generational. And so we want to see now, is that the same as what it was? So this leads or segues perfectly to what is very good. So we have the null and alternative in symbols. So what does this look like? The null says what? Every time you see a null and an alternative, what's the symbol here? Pi, good. And remember, the null is always the one with the equal sign. That never changes. So what does the null say? The null says that the long run proportion of students at home for multi-generational now is what? Did you catch that? 0. Wait, hold on. Oh, okay. Where did you see? Did you see the? Do you see the null statement? What is status quo that you're comparing to? What is status quo? Right? The status quo is 0.35. Do you know why? The blue number is always comparing to something either historical or something or some other school or something like that. Did you see the point? Don't confuse the observed statistic with status quo. Status quo is, see, the hint is this. Read the question. You want to know if this is lower now, which means actually I'm giving you the alternative first. Do you know what the alternative is? Can you write down the alternative? You want to see if the proportion multi-generational now, is it lower now? Which means I'm actually telling you in not so many words that the alternative is pi less than 0.35. That's excellent. So it depends on how your mind works. If you thought of this first, you can. Because this is directly from the question. This has to be in the question. If I don't put this in the question, you can complain. What kind of statistics problem is this? You didn't tell me what you want to test. I need to tell you what I want to test. I want to see whether the proportion multi-generational now is less than what it was 20 years ago. Yes.
Is this facing the 0.35 or the?
Oh yeah, this is a less than because of the word lower. We want to know if the proportion multi-generational now. That's why this definition is very important. Is it okay?
Yeah, I thought that it was different because we're not. Oh, wait.
No, that's fine. I sometimes right when you see students think of things, it's actually quite nice, right? Uh, it's lower now. Did you see? Okay, can I test different? I can, but I want to test if this is.
Oh, can I ask a question?
Yes.
Oh, okay, but it's saying like you're trying to find out if what we have now is lower now, or is it saying you want to know if the 35% is lower now than what we have now? Like, I took it as 35% of Hope students were multi-generational. You want to know if this is lower than what we have now, not you want to know.
Oh yeah, no. I think you have okay. So just take it at face value. See, 20 years ago, 35% of multi. We want to see if it is lower now.
Okay.
So what we're saying, that's why the definition of pi is very important. Pi is the current rate of multi-generational homes, and I want to know if it is lower than what it was 20 years ago. Yeah, I don't play games with students with convoluted English sentences like that, but that's a good point. You can misconstrue it, but I think don't overthink it. It's pretty much face value. So I'm telling you, 20 years ago, 35%. And by the way, it's all fake, okay? I just fake all these things for class purposes. Please don't go report this to other people, okay? I don't know. I don't know. It's a long run proportion. Who knows, all right? So pi is something 20 years ago. I want to know whether now it is what it was 20 years ago. And I want to compare it to whether it is lower. Notice a few things to learn. Even if you don't know the null hypothesis, you can get the alternative first. You get the null automatically by changing this to an equal sign. The null shares the same number. Have you ever seen me write a null and alternative with different numbers? No. It's always the same number, and the null is always the one with equal sign. So even if you get the alternative first, you can get the null. Okay? Good. And so, calculate an appropriate standardized statistic. Which one do we want? It's kind of like there's three types of candy. Which one is it? They are all standardized statistics, okay? They are all standardized statistics. There's three of them. Which one do I want? First of all, what kind of problem was this? Was it a proportion problem or a mean problem? Proportion problem. So you know there's a proportion problem. There are two possibilities here. Can you use simulation where I didn't give you any screenshot? You'd have to use the applet, right? So in absence of that, I would say go with theory Z. See? You have no choice. Unless I tell you, okay, go fire up the applet and get the sim Z and all that. So there's no simulation. So therefore, we're going to get theory Z. Can someone give me the generic formula? I've left it out for a reason. Give me generic first, then put numbers in. Give it to me generically first, using symbols. It's going to involve p hat and pi, let me tell you. All right? So can you fill it in? Theory Z here would be p hat, good, minus pi over the square root of. Actually, I don't know whether by now you have actually remembered this. If you did, it's actually more power to you. It's not the easiest thing to remember, especially when you've not seen it so many times. What comes inside the square root? It's a fraction.
Oh.
Yeah, okay. Does anyone remember? Maybe I'll start you off. You can, but I'd rather you check your notes, you know. Yeah. It does have n inside, but it's not just square root of n. Okay, you're getting warmer. The n is at the bottom. So does anyone remember what is in the square root? All right. Yes. Pi times 1 minus pi over n. Good. And by the way, these are important things you should have in your cheat sheet for the exam, which I mentioned you can do. Because unless you have a very good memory and can remember these things, which I don't recommend, have it in your cheat sheet. Very good. Now, one last thing. Can someone go and put in the numbers here? We have not even talked about any numbers yet. What's p hat here? Now, here's a twist. Don't need to give me a decimal, give me a fraction. Directly give me a fraction from the question. What was the observed p hat in this study? Yes, pi is 0.35. Very good. Yes, 12 out of 46. You talked to 46 Hope students and found that 12 are multi-generational. Very good. And then you know what happens? After you calculate this, you get this. Which table do I use to get a p-value? Since it's theory Z, I use the what table? The same table, yes. Now today, I'm going to teach you, after we are done with this assignment, I'm going to teach you how to get the T table working. But all in good time. Let's now, thank you very much, and use the D table after this to get P value. Very good. Okay, now let's talk about example number two. Where is it now? Oh, sorry. Let's talk about this one. 30 years ago, the average annual income in Michigan was this. Again, fake, okay? I just made some numbers up. 30 years ago, the average annual income in Michigan was this. You want to know if it is different now. See, different. You sample 157 Michigan people, and you find that now the mean annual income in your sample was 35,600 with a standard deviation of that amount. Okay. First of all, answer this. It's kind of like, you need to know what your problem is for you to get better or something like that. So if you must identify what kind of problem is this. Okay, so let me put it here. Okay, first of all, can someone tell me what kind of problem is this? Is this a proportion problem or a mean problem? Very good. Wow, that was fast. Very good, fast and correct. Good. So is this a population problem or mean? But this is a mean problem. Good. I mean, it's so obvious, right? If you ask people what their salary is annually, they give you a number. They don't say yes. So it's a mean problem. Very good. Define the parameter of interest. So you know what I'm going to do? I'm going to copy this, but I'm going to ask you, do I have space here? Yeah, I do. Okay. Can you change something? It's not pi, but what's the symbol? And it's not a obvious. Yes, it's mu. Good. And obviously, it is not a proportion. It is a long run mean. Okay, can you finish the sentence? Remember my slide? Every time you have the word mean, some quantity has to come after the word mean. What are we interested in here? What about Michigan people? What is this parameter interested in? Is the long run mean what? Yes. Now, it will make it less clunky. Do you know you don't have to have the off here? I would recommend taking it away. You know when you can use the off? The mean annual income of Michigan people or whatever it is, something like that. Yes. Good. Or you can say in. That's fine. Right? Don't need to say mean of. Mean directly quantity. Very good. Okay. And again, can I stress? Am I interested in the now version or am I interested in the 30 years ago version? Which one am I interested in? Now. I'm giving you the 30 years ago number as a status quo statement to compare to. That's the point. So we are interested in the one that is now. Write down in symbols. The now says what? And it, of course, involves mu. Did you get from the question what this should be? Right? Can you get me the pair of null and alternative hypotheses that we are interested in here? You all are so good at Google Sheets. So much docs. So much better than I am. I'm very nervous when it comes to Google Docs. Not that good. Okay. What symbol comes here? Tell me first. Tell me what symbol before we go hunt for the symbols. Not equal to what? Because I said I want to see if it is different. Yes. Did you catch that? Very good. So don't worry about getting symbols. Some of you are really good at looking at the symbol box. If you can find that symbol, go put it there. If not, let me teach you. We'll use this. Here's a very nerdy thing you'll learn today. This is a way to say not equal to. Exclamation point equals. Did y'all know this? Okay, if you didn't know that, okay, it's very nerdy indeed, but now you know, all right? Exclamation point equals is not equal to. Don't like it, go hunt in the symbol box and you can paste it there. Up to you. Oh yeah, see, someone found it already, thank you. So you can use this one, okay? Oh, but the thing is, we have not filled in the number on the right side. What does the now say? The new is what? It would make me very happy if you know what number goes here. Which one? There are many numbers on the screen. Yes, it's the 20,000 whatever thing. Why is it not 35,000? Because that's the thing you saw in your sample now, but you are comparing whether now is the long run salary what it was 30 years ago, or is it different? And so this is this, you can give yourself a pat on the back if you understand it, because these are very confusing to many people. They say, why is it not new? That I saw it. Yeah, you saw that. That's not new. That's not new. You don't know new. You are hypothesizing whether now it is what it was 30 years ago. Okay, very good. Calculate an appropriate standardized stat. Which one is it? Can you tell me? Theory what? Yes, we know it's TY because this problem is a mean problem. Yes.
I have a question for the, like in regards to the first question, how would you be able to differentiate, like for the proportional one, whether to use in the or
Very good question. On an exam, if I didn't give you any screenshot for simulation, can you do sim? You cannot. Because on the exam, you don't use applets, Let me tell you that. So if I don't give you a screenshot, you know what I mean by screenshot? Let me show you. If you look at the bottom of this assignment, did you see I gave you a screenshot for that one? Okay. When I give you a screenshot like that, you can use simulation. Yes, a very good question actually. So I want you all to have the option to know that you can do theory Z as well. Very, very good. See, you know what I want. Generic first. X bar minus mu divided by what? S over SQRT or something, right? Yes. Very good. Can you give me all these numbers, what they are? Plug it in. And you know what we're going to do after this? When we finish the third question, I'm going to teach you how to use the T table to get a P value. Because the whole point of a standardized statistic is to lead you to a P value. That's the whole point. See, status quo was 20,500. But what did I see from my sample? What was my sample mean? Very good. See, the sample size was 157. Did you catch the standard deviation and the sample mean? Yes. The sample mean is 35K or thereabouts, something like that. And what was the sample SD? Yeah, 5. Yes, 5. Yes, thank you. That's it. Did you see that? That is why I'm giving all these things together. You have learned 3 things from me. These are 3 problems. And these, if you want to know, students always want to know, what are the exams like? Well, there's something like this. What else can I ask? Well, there's not many things that I've taught you, honestly. Okay, now, then let's do the third. This is going very, very well. So let's do the last one. The last one is a simulation example. And let me paste it here as usual so we can talk about it together. Okay, let me. Now, I believe you're going to need to look at the screen because the resolution is very, very poor indeed. I'm so sorry. The picture really doesn't. If you can read the p-value from there, your eyesight is better than mine. All right. Don't bother with that. I will show you on the screen so you can. Okay, but let's answer these things first. 100 years ago, 2% of women in Michigan did not change their names when they got married. Okay. You want to know if this is higher now. Did you catch that? Okay. 100 years ago, 2% of Michigan women did not change their names when they got married. And you want to know if this is higher now, you sample 58 married Michigan women and find that 5 of them did not change their names when they got married. Very good, I can see. Is this a proportion problem? Yes, of course it is. Because you talk to a married woman and ask them, did you change your name? What are you going to say? 5? I didn't ask you how many times you changed your name. I said, did you change your name when you got married? The answer is yes or no. So it's going to be a proportion problem. Define the parameter of interest. Every time you see parameter when it's a proportion, these words should fall out of your mouth. The long run, what? What's the parameter here? Is it a mean or a proportion? What are we interested in? Proportion. Is the long run proportion? Yeah. What about okay? A proportion has to be measuring something. The long run proportion of women who okay, this is acceptable. But here's a word of advice. Since the whole thing is phrased in terms of did not, always align your definition to the data that's given to you. The long run proportion of women who did not change their names upon marriage. And I would be more specific. I would just say which women, the Michigan women. The long run proportion of Michigan women who did not change their names upon marriage. Now, yes, now, because are we interested in 100 years ago? We already know what the rate was 100 years ago. Did you see that? Very good. And the symbol for this would be? Because it's a long run proportion, the symbol we use is always pi. Very good. Write down the null and the alternatives. The null says H naught colon that pi is what? What is status quo? You're comparing what it is now to what it was. That's right. The 2% is the status quo, and that would be 2%. When I see 2%, I think automatically of milk. That's terrible. This is called a Freudian slip. Right? So I think you all know what kind of milk I buy. Right? But anyway, and what we want to know if this is high. Good. See, we want to know if it's higher now. So higher now. This is really good, you know. Now, if you can answer me number 4, that will make me very happy. Why is it not appropriate to go the theory route? We know that proportions, there's 2 options, right? What is problematic here that you cannot or should not? Yes. We don't have enough successes. Very good. How many do you need? At least 10. So can you define it correctly without using the word successes? We needed at least 10 what? Don't use the word success. All right. You know that meme? Tell me you're from Michigan without telling me you're from Michigan. So it's like, tell me what a success is without using the word success. Can you tell me? You need to have at least 10 women who what? What must be true about the 10 women? We needed at least 10 women who did not change their names. That's right. Did we have that? We only had. Actually, how many women did we talk to? 5. And no, we talked to 58 women. Only 5 didn't change their names. That's not 10. Therefore, you did not meet the VCs. And so there's this, if you watch infomercials, right? They always say, are you still doing things the old way? And then they'll make it sound, it's wrong, right? And then if you do the ding, the bell will ring. They still do this in 2025. It's all wrong. So this is like, you didn't make the VC. I hope you all don't mind. I don't know. Some students don't like it when professors do things like that. But I honestly, I think it gets points across to the class. And I used to have students, get there's a green check mark. I like that one, and a red X. So you can also do that. So we needed at least 10 women didn't change their names, and we didn't have that. So you cannot use theory. You have to go the SIMSI route. which is why I have to give you this screenshot. You have to use simulation to do this problem. So unless your eyes are like an eagle's, right, you probably have to look at the screen. I don't think my screen is much better either. It's really small. So it's very, very hard for me to, even Google has given up. Hold on. What? What is it? Okay. If you want to use simulation, can you tell me what numbers go where? What should I fill in my pie box? Tell me carefully. I'm not going to type anymore. You tell me orally. What goes in the pie box? Status quo, right? What is the status quo value of pi? 0.02. What goes in the sample size? How many women did I talk to? 58. So 58. What's the number of applications? The famous number always. 1,000, and you can see that here. It's 1,000. Good. What goes in the extreme box? Can you give me a fraction? You don't have to convert anything. 5 over 58, because that's what you saw. And finally, can someone quote the sim-based p-value? Did you see it? It's not in purple, but you have to imagine it's in purple. What's the sim-based p-value according to the screenshot? Did anyone see it? It's a very important number. It gets repeated, you know. I'll give you that hint. It gets repeated a few times. The sim p-value is 0.166. Did you get that? It's here, it's not here. This is the red number. This is what you observe. The purple number is here. This is purple, this is purple. I know I'm gaslighting the class. It's not purple, but it's purple, okay? That's definition of gaslighting, right? So this is purple, okay? It shall be purple. Okay. And what does SimZ look like? Anyone want to try? What goes on top? Red minus blue, right? So what's red here? Give me a fraction. You don't have to give me a decimal. 5 over 58. And what's the blue number? Status quo is 0.02. And what's the green number? Okay, this one really is a challenge your eyesight. Did anyone find the green number for SD and the null distribution? Can you see it from the sheet of paper? I don't think you can.
0.03.
Wow, really? You all have better than 20/20 vision. Okay, it's 0.03. I don't know why the resolution is so bad, honestly. Don't worry, on exams it won't be like that. Okay, 0.03 is the green number, the SD of the knowledge. Did you get that? So that's SimZ. So the reason why I gave this example is because this social phenomenon of women taking the spouse's last name is quite uniquely American and European. Let me tell you, this is not practiced anywhere else in the world. In Malaysia, when a woman marries, she doesn't change her name. Yes, she is known as Mrs. X, and X is the husband's name, but there's no legal name change at all. So I was very surprised when I came to America how much of a thing it is. In fact, it is a point of sometimes some tension in a relationship if you read this. So, because it is the expectation of many men, especially in the Midwest here, that this should happen. So I was best man when I was in grad school, and you know if you're best man, you're probably a good friend of the person you're best man to. So I was a little bit of a chill, okay. So I just asked, I said, because I was shocked, you know, at the wedding, there was actually a formal procedure. I thought this name change thing wasn't even legal. I thought it was just a societal thing. It's legal. Your name really does change. So I said, is it important to you that your fiance, when you all get married, change it? He said, of course. So I said, why? He couldn't tell me. He did a what about this? Do you want your wife to change her name to? I said, that's not what I asked you. I said, why is it important to you? And he couldn't give me an answer. He said, it shows that she wants to committed to joining the family. I said, yeah, aren't you committed to joining her family? Why is it in one direction? And then there are no good answers. Basically, I believe it's a sexist practice. It is. And it is so ingrained that I think, especially in the Midwest region, women don't even give it a second thought, or sometimes they say, "Why fight it?" Right? I think honestly, the proportion of women that actually wouldn't want to do it is actually quite high, but they don't want to rock the boat, and they say, let's not die on this hill, kind of thing. But let me tell you, as a statistician, this is a disaster. Because statisticians are all about data, and when a woman changes her name, historically, what her maiden name is begins to be forgotten after a few generations. There's a multi-generational amnesia about it. Who knows? Do you know the maiden name of your great grandmother? You probably don't, See? So there's lots of information, and that's a statistical sin. So from a statistical point of view, I mean, I'll tell you, we in Malaysia we get a lot of American TV. And because TV shows are expensive to buy, you know what Malaysia would do? They would buy a lot of failed American sitcoms, those that don't make it past season one. So I watched a lot of American TV, and the problem is they have credits at the end, and I'm a person that likes names. And so I used to look at the credits. I know people usually go to the bathroom, but I look at the credits. And so I I would notice a lot of people with the same last name who write the sitcom together. So I said, why do so many men work with their sisters on things? And at that time, I hadn't come. I said, that's very odd. Usually, people don't collaborate with their sisters professionally. It's very rare. Actually, I found out later that they are with their wives, right? Because of this changing name thing. You know what I thought? I thought, why do so many? Because usually brothers and sisters don't have very close relationships, especially there are exceptions. So I was so surprised. So many siblings work together. I didn't know that they were actually married. Okay, but anyway, so this has a long history, and that's why I picked this example. Okay, but again, these numbers are made up. I have no idea what the fraction of Michigan women is who don't change their names. Right? These are just things that I made up. Okay, I did promise you I'm going to teach you how to read the T table today, and that's what we're going to do. So, can I have to motivate this? Let's go back to our sleep data. See, this number is correct, but it is so big that it's not going to prove my point. So I'm going to make another T value, and I'm going to teach you how the table works. Uh, yeah, it's such a pity, that this number is so big that it spoils my punchline. But I think I'll start with this one. That's okay. So the first thing you need to realize about a T table is there's this thing called the degree of freedom. So the first rule you need to learn is, what's the rule for the degree of freedom? It is always sample size less one. Very easy. So in our class sleep data, how many people did we have? See, AI is so dumb. It thinks n minus 1 is 1. It's not that powerful, It cannot detect what n is, which is actually a good thing, because if AI could find what n is and tell me, I'll be freaking out right now. It couldn't. Does anyone know what n is for our class data? Anyone remember? It's on the screen actually. How many people responded to our, oh, it's there, 20. There were 20 people who responded to the sleep data set. Therefore, the degree of freedom is 20 minus 1, which of course is, this one AI knows, right? 20 minus 1 is 19. Okay, good. That's the first step. So let me show you how the T table works. So the T table is, okay, where is it? Okay, the T table is on Moodle already. Again, I recommend you print it out. It's very frustrating to do these things online, but for today, I'll show you. Okay, so the first thing about the T table is the degree of freedom. Do you see a column on the left side? This is the degree of freedom. So go to 19. Okay. N minus 1. So go to 19. I'm going to highlight the whole row for a reason. Okay, I want you to stare at the numbers in this row. What was our T statistic calculated for our class? Anyone? I think 5 point. What did you see? See, 5.903. Did you see that? 5.903. Now go back to our table. Do you realize that as you travel from left to right, the numbers are getting bigger? Where's 5.903? Literally off the chart. That's where the phrase comes from, off the chart, right? So 5.9 is off the chart. So what does that mean? Look at the last number. Okay, look at this column. Do you see a 0.00005? Okay. What is that? Well, the picture helps you. This tells you that the tail area is going to be smaller than this because you are so far out. This area is now so small. That's your p-value. Was that easy? The p-value is less than 0.0005. You can only give me a range. You don't know exactly how much. It's after this, so it's not. It's even smaller because you notice these areas are getting smaller and smaller. So this picture is not an on the left picture. This table is actually easier to use. It's right. It's tail. It's the tail, and you know p-value is all about the tail. So this area is less than 0.0005. That's all you can say. So I'm going to type that in Scratchpad. So the p-value here that's all you can say. You cannot give me an exact one, but who cares? A range is enough. That is why your homework problems are all ranges. This table works as ranges. Okay, so with this on, let me give you a few pretend scenarios and pretend degrees of freedom, and we'll work through this. And once we are done, we are done for today. I want to work a few cases with you so that you can do your homework. Let's say I got a t value like 2.759. Let's make something up. And let's say the sample size was 29. Oh, no, let's go with something else first. 23. Okay. So first of all, establish what's the degree of freedom. What's the rule? The degree of freedom is always n minus 1. Good. Which means it's 22. Good. So the first thing you need to do is go to the table, make sure you are on the row that says degree of freedom 22. Highlight everything. It just makes it easier. Okay. What was our fictitious value of t? See, I'm just 2.759 for some reason. Okay, 2.759. Where's 2.759? Well, it's not here, it's not here, it's not here, it's not here, it's not here. It's between these two. 2.759 is between these two. Why is that important? What areas are associated with this column and this column? So now, I myself must be careful. This is the fourth and third columns from the right. So it's between the fourth and third columns. What's the area? Fourth column from the right, 0.01 and 0.005. So therefore, what's the p-value? The p-value is between those two numbers. Your number is stuck between two things, and so the area is also stuck between two things. So the area is between, and I'm going to copy this. The area, therefore, the p-value here is between this and this. Did you get that? I'll be doing a few more examples, don't worry. We'll do one more. Okay. Let's say I got make something up. Okay. Okay, something like that. And let's say n now is okay. What df should I use? Not 22, clearly. So what should it be? 27. So look at our table. Do we have 27? We do. Later, I'll tell you what to do when you don't have a value, okay? So look at 27. Highlight everything. Okay, what was my t statistic again? I can't even remember. I made something up. Okay, 1.976. So where's 1.976? 1.976 is between what and what? This and this. Did you see that? So second and third columns. Therefore, your p-value is between. Can someone type it in so I know that you know what you're doing? The p-value will be between what? I don't want to say it. I want to see if you can identify it yourself. That's right, 0.05 and 0.025. If you look at the table, between those two, that's it. It's a range. And that's all you need. All you need is a range. You don't actually need the exact p-value. See, the z table does give you exact p-values, but t works differently. All right? Okay, very good. So I guess I'm now going to tell you what happens if your t is negative. Okay. Do you know? Here's something nice. If your t is negative, do you know that what you do is this? The table only has positive numbers, right? Pretend it's positive, get the tail area, that's your answer. Did you see that? If you get a negative value of t, pretend it's positive, get the tail area, and just report the tail area the same way. And now let me ask you, what about if I wanted a two-sided test? Does anyone have any suggestion? You know that a test can have a two-sided alternative. What will happen to the p-value if I wanted, all these are one tail. If I wanted the two-sided equivalent p-value for the equivalent test, there's two-sided, what do I need to do to that answer? Multiply by 2. But this is a range, so you multiply both ends of the range by 2. So the two-sided p-value is between what? Anyone want to try? If your test is one-sided, that's it. The table gives it to you immediately. But if your test is a two-sided alternative, you need to multiply both ends of the range by 2. What's the answer? What happens when you look at that range and you multiply by 2? Anyone? And then I'll tell you one last thing after this. Anyone know what is this? Okay, do you know what I mean by multiplying both ends of the range by 2? Okay, if I tell you one t-shirt I bought costs between $5 and $10, and I buy 2 of them, what can you say about what I paid? I now, I took one t-shirt between 5 and 10, 2 t-shirts are between what? 10 and 20. Can you do this? See, always use money. It helps. See, 0.05, you times 2, 0.1. This one you want to, okay? Okay, one last thing. Have you thought about this? What if the degree of freedom is not available? What do? Sit and cry, right? No. If a DF that you need is unavailable, call again later. No. Right? If something is, oh, yes. Yes. How did you know? That's correct. You don't round up, you round down. Very good. So let's say, okay, let's say you needed, I don't know, 44. Not there. Don't go to 50, go to 40. That's it. So I'm going to type this out. If a particular degree of freedom is unavailable, round down. I'm going to say this 5 times, okay? Because students always forget. Down, 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 down. Round what direction? Up or down? Down. Okay, good. Have a good weekend. No. What am I saying? See you Thursday. That's right. Okay. I'm so sorry. Let me